welcome everyone to my talk. I'm really happy to be here and share my knowledge and work with you. So I hope you enjoy it. So today we're going to talk about Physiologic. Physiologic is an AI framework. Basically, it can help you to model or handle uncertainty on the data. And also it can be used for give solutions to or create systems that require human-like decision-making solutions. So in real world, basically, it can help you creating controllers or help you do some processing in vision computing. So, but before explaining all these concepts, let me introduce myself. My name is Aldebaran Alonso. I'm an embedded systems engineer at Valiot, which is a company focused on Industry 4.0. We basically optimize the production process of a manufacturing company by using AI and IoT. So my main job there is that maintain and develop new features of our edge device, which is the device that is right on the corner. It's a nerve-based device, therefore it uses Elixir. And we use this device to post data from industrial machinery, just like sensors, PLCs, SCADA systems, and so on and so forth. But in some times, we require to do some or compute inference using the shop floor context and the human knowledge of the operators. So how this device can do these kind of things? Well, this is basically what we are going to talk today. Okay. So this is the content that I would like to cover today. First, we will understand what Physiologic is by explaining the problem that it aims to solve. Then we are going to review a comparison between classic and Physiologic. And then we will discuss the elements that requires Physi systems in order to make a computer understand human statements or sentences. And with that said, we will use next the library that we developed, which is Flex, Physiologic in Elixir, and we will showcase these concepts in Livebook, and I will show you how you can create Physi controllers and apply machine learning to it, because we're going to discuss the advantages and disadvantages about the framework, and machine learning could help us overcome those disadvantages. And finally, we will discuss about future work about the library. So yeah, the introduction, let's understand what Physiologic is. Basically, the problem is that we know that common software works only on problems where the data is complete or exact. Otherwise, it provides a wrong solution, or maybe it will crash and give no solution at all when the data is incomplete or uncertain. I will explain later on what I mean with uncertainty. Well, uncertainty is basically when the context of the data is not specified. For example, if you say to a computer that a motor is running very fast, well, the computer doesn't know what it's trying to do, because it is not a real number that the computer can handle. So, and this is because also the concept of very fast is also relative between different human opinions. So that's what Physiologic wants to solve or to help you handle. And basically, these terms are based on the human knowledge. Therefore, we need a framework to help us to make the computer understand the knowledge of the human. So that's the problems that Physiologic aims to solve. Then let's start with comparing what classic logic is. Well, classic logic is a topic in mathematics. It studies how inferences are made in a reasonable, coherent, and explainable way using exact data. We all know the truth tables, how they work. We know the operators, the NOT, the OR, the XOR. There is nothing new here. But what is Physiologic? Physiologic is a topic of AI. It also studies how inferences are made in a reasonable, coherent, explainable way, but using uncertain data. This is the catch. Fuzzy logic gives you a way to model the uncertainty. And how does these frameworks does that? We can start by explaining how is this approach using the set theory. Basically, the set theory is basically trying to describe if an element belongs to a certain set. The certain set will have its own features. So let's do some examples with this. The first example is just trying to check the color of this card. Does this card belongs to the set of black cards? Well, it's pretty easy. It does. There is no problem here. I think everyone here in the room will agree with me. Also, a computer is quite easy to understand this color because it's a matter of setting just a simple threshold, and that's it. This other example is quite a little bit of the same. We are asking if it belongs to the set of red cards, and yeah, it does. But what is the common thing of these examples? Well, basically, they are very synthetic examples. They are not real. They can be described as binaries by using thresholds, and they can be easily understood by a computer. But what happened when we use a real-life example? Well, if we do the same questions that we discussed previously, does this card belongs to the black cards or the red cards? Well, it's quite difficult because if we use the definition of what a set is, well, these cards will have its own set. Maybe it's the set of, I don't know, the unknown colors or whatever. So the other problem is that this card cannot be easily mapped or described as a binary, and binaries basically are for computers. Computers work with binaries. But what is the problem with binaries? They are absolute. There is no middle point between 0 and 1. But we as humans, we can do better. We can add relativity to it, and we can say something like this. This card basically belongs to the set of red cards by 10%, and also belongs to the black cards by 90%. What is the problem of this slide? Basically, is that this is my opinion because I do the slide, but maybe someone here will argue with me and say, hey, you are missing the set of the orange cards, and the set of red cards is wrong, it's like 50% or whatever. So we as a humans, we need to agree in how we are going to define this kind of relativity. And this idea basically comes from this guy right here, which is Lotfi. This guy introduced the theory of fuzzy logic as well as the Z-transform, but that's another topic. And he said that we can associate to the set a membership value of how these elements or the percentage or how the element belongs to a certain set. So the catchy thing here is that he proposed using a mathematical function just to map this value. So this mathematical function can have any shape that we need just to describe the behavior of the element being part of the set. These kind of shapes can be either a Gaussian bell, can be a triangle, can be a trapezoid, or whatever. And this can be a pretty good help for us. Because, well, in this slide, I show you an example of how these things work. The first membership function is a threshold. This means that it's a classic, is using the classical logic approach, and the one that is below is using another function that means that we are on the fuzzy logic. So in this case, we are talking about the variable of the height of the person, and as we can see, the first graph, which is a threshold, it works well when we are using values that are not near to the threshold itself. Let's say, an example, if the threshold is 2 meters, and we have a person that is 2.05 meters, it will be successfully classified as a tall person. But what happens when we have a value that is near to the threshold, that is 1.999? Well, the system will classify it as a shorter person, and that's a problem because we as a humans, we know that that logic seems wrong, and it fails for us. But if we use a different membership function, like a CMOI function, the logic seems to improve the way that the human think, because the same guy that is 2.05, it will be mapped as a tall person, and the other guy that is shorter, it will also be mapped as a tall person, but with a less degree of value. This makes more sense for us. And well, the next slide shows you how multiple fuzzy sets work together to map the behavior of a variable. In this case, the variable is the temperature. We have 3 fuzzy sets here. The temperature, the cold temperature, the warm temperature, and the hot temperature. In this example, we are asking about a temperature of 0 Celsius degree. This, if I ask someone that lives here in Orlando, well, basically, obviously, he will tell you that it's a cold temperature. But if you ask the same question to someone that lives, I don't know, in Alaska or something like that, he will tell you that it's not. It is a warm temperature for him. But both of them will agree that no, it is not a hot temperature at all. This is a way that we can see how these fuzzy systems are working together to describe a behavior of a fuzzy variable. So now that we understand how fuzzy sets works and how can we model a variable using this theory, in order to do inferences, we need to have operators to do that. And we can extrapolate the idea of normal operators by using, for example, the AND operator can be related to the minimum operator, yeah? The OR operator can be mapped as a maximum operator, and the NOT operator can be mapped as a minus operator. Using this, available us to do inference using the membership values of every given fuzzy set, and because they use values between 0 and 1. But if we use the binaries between that, we can have the classic values of the fuzzy tables, the truth table. So we define what a fuzzy operator does. Now we can define rules and statements that a human can understand, and we can describe how the computer should behave. So in this case, the first rule shows a structure of an antecedent and a consequence. Just as if the temperature is normal, then the fan speed is moderate. This means that it has an input and an output here in the right side. So for the rule number 2, we are making a more complicated sentence, and we use the fuzzy operators here. And here we are setting that if the temperature is hot and the demand is high, then the fan speed is faster. This means that we want to make the computer to handle this logic. So, but how can a computer understand this? Well, this is fuzzy systems were made for that. So how does the fuzzy system works? It has different phases that we will describe next. So the idea here is that we in real life have raw data, floats, and crisp inputs. So the first step is pass those values into the fuzzy realm by making a fuzzification phase, and then we can compute all the rules that we defined previously, and we will have output, but in fuzzy realm, which has membership values for the given sets that are related to the output. Then, since we are on the fuzzy realm, we have to transform them into the realm of the real world, just to have the values that help us for the problem that the system was designed. I know that this is kind of confusing, but maybe an example can help you understand the point of this. In this case, this is an example that I found in MathWorks, and it's a system that computes the tip of a restaurant. Well, basically, the system is based depending of the service and the food, how it's going to compute the output. So the first step is defining the fuzzy sets of the input. In this case, the service can be either good, either poor, or maybe can be excellent. And the food has two possibilities: can be a rancid food, or can be a delicious one. So the next step will be defining how the output will be, and defining the fuzzy set shape, or the membership function shape. And in this case, the output, that is the tip, can be a cheap tip, can be an average tip, or can be a generous one. So now that we defined our input and output, we have to define how the system is going to behave. Therefore, we are going to define the rules that the system will need to execute. So the first one is, if the service is poor or the food is rancid, then the tip will be cheap. But the next rule will be that if the service is good, then the tip will be average. And finally, the last rule is that if the service is excellent or the food is delicious, then the tip will be generous. So we have all the components that a fuzzy set requires. The next step will be to execute this example. In this case, we have a service of 3. This means that the service is between poor and good, but we know that it is not an excellent service. So we are like defining that with using our knowledge, we know that it's not going to be a generous tip. But the food, on the other hand, it is quite delicious because it has a value of 8. Then the next step is to execute these inputs into our fuzzy sets, which means that we are going to compute the every membership function that are related to the fuzzy sets. In this case, we can show that they have different values. Then we have to compute the rules. We have several operators here, and we define that the operators are, in this case, for the fuzzy realm, the OR is the max. Then we compare the pure is a value of, I will say something like 0.2, but rancid is 0. Then the maximum value is the one that has the poor set. This value, basically what it does is weighting or ponderate the output of the fuzzy set. That is on the consequence of the rule. Therefore, the rule is not like the whole triangle. It's like just cutting down the parts that are related to the statement that was poor. How much poor does this service is, in fact. So the same goes for the other sets. We compute the set. In this case, we don't have any operators, therefore it passed directly and just threshold the fuzzy set. In this case, we execute the rule, and then we have all the membership values of our output. We have to combine these rules in order to get the real world value that we need. So we can do, in this case, we do the aggregation method. Is applying the max value between every graph or every fuzzy set. We will get a figure just like this, and we can do the fuzzification phase, which means that we can use a mathematical method just for this case. Use the centroid, which means that we are like computing the center of mass for setting out the output that we are going to be using. So for this case, it's like a 16%. Well, this is basically the theory. Now we are going to do like a demonstration with how do I say, livebook. So in this case, we have this variable, this library, which is we have this link, and all the things that we talked today, like how to define a fuzzy set, fuzzy variables, membership functions, all of these things are covered in this library. We have multiple membership functions that you can use depending on your own case. And we can also, since Elixir is very flexible, we can also define our own operators. For example, the AND operator, we use a specific syntax just to do the mapping between the one that is on the classical AND and the one that is the fuzzy logic. For the rules, we have an extra, we have two kind of syntaxes. One is defining as an anonymous function, and the other one is like in a tuple way of showing how the system should be computed. The inference systems, for the example that I talked previously, we use the Mandani approach. The Tagana or Sugeno is another one, but for today we are going only just to see the Mandani. So, how to design a fuzzy controller? Well, the schema that I show you here is basically what we were talking on the previous slides. And the catchy thing here is that we are going to have, like, as an input, the set point of a desired variable. So since we can have a feedback, we can compute the error of how the system will be behaving. Then if we have the error, we can do extra or more interesting things like creating or computing the derivative of this error and have more control by taking more in consideration, like how the error is changing in time. So the first thing to do is do some imports. Then we have to define the fuzzy sets. In this case, for the error, which is the first input, it has like three fuzzy sets. The one if referring that the error is too hot, or it's just right, or it's too cold, basically. Then we define the sets for the derivative of the error. This means that we would like to have or to know when the error is getting hotter, or it's not changing at all, or it's getting colder. Then we have to define how the output needs to behave, or the fuzzy sets of the output. And the output of this controller is basically trying to call the system, try to do nothing itself because we are right, or try to hit the system. So now that we have all the sets defined, we need to create our variables. That is only make the relationship between a name of the variable and the fuzzy sets that are related to it, and also define if the variable is an input or it's an output, which in this case is if it's an antecedent or if it is a consequent. Then we have to define how the system will behave by writing the rules of the system. I am going to explain the first one. As I said before, we define specific operators. In this case, for example, we have two antecedents and one consequence, two inputs, one output. And the first input is basically saying that if the error is too hot, and this is the AND operator that we defined, the derivative of the error is getting colder, then this is the then operator. The consequent will be cool, basically. So in this case, we define all these 9 rules in these syntaxes. It also can help you like mapping the rules as a matrix to be more like human friendly. And then we have to create the system. The system, basically, you only need to relate or to tell what are the antecedents variables and what are the consequent variables. Also, you define the rules there that it needs in order to compute. So now we can compute the system and see how it works. In this case, I am showing values in the input vector as -1 and -2.5. The -1 means that the error is between too hot and just right. And checking the derivative of the error, that is -2.5, it's basically between getting hotter and not changing at all. So the following rules were fired or can be triggered, will be triggered, and we can say that all the consequences tell the system to cool, but only one is telling him that you don't need to change. So the output of the system will be, yeah, cool, but not at full strength. Full strength will be like minus 100. In this case, the system tells, yeah, like cool, but not as much as it can. In the other example here, we basically tell that the error is 0, is just right, and the derivative of the error is not changing at all. So the system, since the only rule that it's fired is telling that you should not do nothing, just to stay like control in the set point that you want, then the output will be 0. In this case, it's basically the same as the other, but changing the sign, and it's telling that the error is between too cold and just right. So the derivative of the error, it's the same thing. It's getting colder and not changing at all. So the output in this case is like minus 63, because it's the same use case, because the rules are telling the system to start heating, but there is one rule that specifies that you should not do anything. So the way that the system thinks is, yeah, I'm going to heat, but not at full power. So if this controller needs to be tuned because it doesn't fit all our requirements, the only way that you can do, or the only thing that you can do to tune this system, is basically modifying the rules to make something more significant for the application, or changing either changing the fuzzy sets or changing the shapes of them. You can change the shapes or increase the number of fuzzy sets. For example, in this case, I create only 3, but if you create like 5, you can be more specific of what the problem is, of how the system, how the variable will behave, basically. So if there is a way in which we can do this in an automatic way, and this is applying machine learning to it. Basically, oh fuck, this is join system. Okay, yeah. Since someone had the great idea to think this system as a neural network, so they put like an analogy of the framework that I showed you before into a way that a neural network can work. For example, in this case, this is the fusification phase, then the implication, the normalization. This is part of the inference engine, and then the fusification phase. The aggregation is the thing that I told you before, like combining all the rules. So in this case, these guys, basically what he were thinking is setting down several layers like constant, and make some layers like dynamic. So what they are basically trying to do is like automatically modify the fuzzy sets, just changing their shapes, and also modifying the rules by changing the outputs here. So the same thing, we have to import, we create the training data here, then we define the input variables, we define all the sets. Here is a catchy thing, you can only use a bell function because we need to apply like mathematics here, and it requires some derivatives. So only we can use function that can be derived. So now we define all the outputs. Here I just create or use the membership function of a linear combination. This means that it's like a combination of the input. And in purpose, I just set these values as 0, and we will see what outcome we will have. Now we declare all the possible rules. and we create the system. So we created the system as a GEN server, and this will give us a PID. Then we get all the executions, basically by having all the inputs and compute the system, get the predicted data, and as we can see here, well, the line on blue is the target function, and the circles are the output of the system. You can see that we are just predicting zeros. This is because the first state of the system is only zeros. But now we can apply a training phase. So in this case, I already evaluate this function. We have like 100 epochs just for the training. And we do the same process here just to get the data to be plotted. Okay. And here it goes. Basically, we have a better behavior than the last one. This is more accurate, like the target was. Basically, that's a way to integrate machine learning into the framework. Okay, future work. This library, we wrote it like several years ago. So in the time, we don't integrate NX because it doesn't exist, basically. But we need to add NX just to have a better performance. We also there is also another topic in fuzzy logic that is an extrapolation of the concepts that will help us create even better systems. And yeah, that's the thing. I would like to thank all the ecosystem because it's pretty fun to develop on Elixir. And yeah, I would like to thank Valiot because it is my sponsor for this talk and make this thing possible. And yeah, thank you for hearing me out.